Alright, Honors Algebra, Chapter 5, Section 4, Medians and Altitudes. So, a median is a segment of a triangle is a segment from the vertex to the midpoint of the opposite side. Since there's three sides of a triangle, there are three medians. The point of concurrency, or the point where all three medians meet, is called the centroid. Point of concurrency of the medians of the triangle. And remember, the point of concurrency is where multiple three or more lines meet. In this case, three or more medians. Okay. The point of concurrency is also called the center of gravity because it's at where the three medians meet at the centroid. It's just perfectly balanced since it's center of mass, center of gravity. So if you had like a pencil, if you created a triangle and tabulated its midpoint, you would be able to balance it perfectly on anything. Okay. Which leads us to theorem 5.8, which is a concurrency of medians of a triangle. So CONC. And what that says is that if I have a triangle, and I have my three medians, then the point at where they meet, the point of concurrency, I could do better than that. Let's see. The point at where they meet a little better. We'll call this point P. Right here. The point at where they meet is 2/3. So here's the point of concurrency to the vertex. So the point of concurrency to the vertex, this distance is 2/3 the distance of the entire median. That is the concurrency of medians theorem. D, E, and F. So if I was looking at AP, so for the point from the point of, or the centroid rather, this point of the centroid, or the point of concurrency to the vertex. So this is AP. That would equal 2/3 the distance of the whole entire median segment AE. If I was looking at the point of concurrency to the vertex C, PC, or CP, that would equal 2/3 the distance of the entire median CD. If I was looking at the point of concurrency to vertex B, BP, that would equal 2/3 the distance of the whole entire median, BF. So if you think of this in thirds, I can find out this last one. Since it's 2/3, I have to add it plus some fraction to equal 1 whole, right? And 1 whole can be considered 3/3, since we're talking about thirds. So what is 2/3 plus that blank? 1/3. So this last distance from the point of concurrency to the midpoint, from the opposite side, this guy would be 1/3 the distance. So you can get other equations from that. You can get, well, if that's the case, then from EP, and this isn't in your book, by the way, but this is something that you can sort of infer already. EP is 1/3 the distance of AE. You can say DP is 1/3 the distance of CD. And you can say FP is 1/3 the distance of BF. You can also get that from that. Yep. So concurrency of medians have a triangle theorem. So with that, you can do various mathematical stuff, mainly fractionary stuff. So in this case here, they give me that SC is equal to 2100. They give me that BT is equal to 1000. And they give me that PT is equal to 800. So number one, they want me to find PS and PC. All right. So they give me SC, which is the entire median. I am told that they're medians, right? Yeah. Which is the entire median. So I'll just use the equation PC is equal to 2/3 SC, which means PC would equal 2/3 of 2100. So PC would be 21 divided by 3 is 7. 7 times 2 is 14. 1400. So PC equals 1400. And there's two ways to get PS. One way is you could just do the 1/3. So I can say that PS is equal to 1/3 SC. So that means that PS is equal to 1/3 of 2100. So the PS is 700. No, it makes sense because 700 plus 1400 is 21. Or you can just subtract 21 minus 14. 2100 minus 1400 must be PS, because that's the remainder that's left, and I already know what the whole distance is. So I can use the segment addition postulate. And that gets me 700. Either way, I'll get 700. All right, so that's number one. Number two, they tell me that BT is 1000, so they want TC and then BC. So since I'm told that this is the median, I know that this guy and this guy are the same. So if BT is 1000, then TC is also 1000. and TC is 1,000 because it's the midpoint. So then if I know this is 1,000, this is 1,000, I just add them up. So I could say that BT or BC is equal to BT plus TC, which is 1,000 plus 1,000, which equals 2,000. Then for PT, okay, the PT is 800, and then they want to know AT and then AP. So, since PT is equal to 1/3 times AT, I could say 800 is equal to 1/3 times AT, multiply both sides by 3, and at AT is 2,400. Again, I can get AP two different ways. The first way is just to say, since I know this is 2,400, I can say that AP equals 2/3 times 2,400 times AT, which is AP equals 2/3 times 2,400. 24 is 8 times 2 is 16, so that means 1,600, and again that makes sense because 1,600 plus 800 is 2,400. Or I can just subtract from 2,400. You can say that 2,400 minus 800 equals AP, which is 1,600. Either way, I will get there. Okay, so that's medians and centroids. Alright, then we have the altitude. And the altitude of a triangle you guys kind of already know what the altitude is. When you do the equation for area of a triangle, base times height, altitude and the height are pretty much the same thing. So altitude of a triangle is a segment in a triangle that is from the vertex to the line containing the opposite side. So what does that mean? I'll tell you what that means. So there's 3 scenarios with that. Scenario number 1, I have acute triangle, right? I have this vertex, which is this line that goes from the vertex to the line containing the opposite side. Oh, I forgot to say. Yeah, I wrote this wrong. Segment of a triangle. Segment in a triangle, I should say perpendicular. It's a perpendicular segment a triangle that is from the vertex to the line containing the opposite side. Okay, so here's the vertex. It's a perpendicular line. Here's the opposite side, but if I can draw a line through this guy, this is the line that contains the opposite side within it. So that's where this comes from, and there's a reason why that is, and I'm going to get to that in a second. Then we have a right triangle. And what's neat about right triangles is that the altitude is one of the sides. So look at that guy. And here's the line containing the opposite side here. There you go. Yeah. And then you have an obtuse triangle. And this is why we say the line containing the opposite side. Here's the opposite side. If we from this vertex, if we look at this vertex, and we were to draw this line containing the opposite side all the way through, like so, we can come down from our vertex, and our altitude doesn't necessarily have to be within the triangle. Okay, so there's our altitude here. And we can do the same thing for all of these guys. So this guy here, and then the opposite side of this guy is here, so this isn't so bad. Here, and then the opposite side of this guy is this guy. So I can draw its line all the way through like that. And let's see, make a 90-degree right here, like so. So obtuse would have two of these guys, and they would eventually meet way out here. We're going to get to that in a second too. The reason why it says line containing opposite sides for obtuse triangles where our altitude can be outside of the triangle. So point of concurrency on a altitude of triangles, which got to our next point. The lines containing the altitude of a triangle are concurrent. Well, we know that, meaning that altitudes can meet at a point, and don't necessarily have to meet at a point that's inside the triangle. When we talk about concurrency of altitudes, they also have a name, and the name that they give is the orthocenter. So the orthocenter is the point of concurrency of altitudes. Point of concurrency altitude of triangle. And just like I wrote before, the orthocenter for an acute triangle, it's on the inside, just like a perpendicular bisector when we did incenter. Point of concurrency of altitudes of a right triangle, they meet on one of the vertex, so because there's two on each side, and the third one down the middle, and then the point of concurrency of an obtuse triangle will be outside of the triangle. This guy would go this way, this guy would go this way, and this guy would go this way. So if you look at it, here is the line that contains the opposite side. Here's the vertex, and it goes up here, and this is the point where they meet. And here's the line containing the opposite side for this vertex, and they meet here and up there. So they meet outside. Okay. Here, isosceles triangles is a unique situation. What we have an isosceles triangle. So this guy and this guy are the same. And we draw the altitude of an isosceles triangle. What's unique about that is that the altitude is also the median. It's also the perpendicular bisector, and it's also the angle bisector, all in one. And also in equilateral triangles, all three vertices are the same in terms of that. So, so isosceles and this would be from the vertex. Remember, these are the base angles here. So this doesn't apply to the base angles. And then this is the vertex. So the median the altitude perpendicular bisector and angle bisector are all the same. From the vertex only. So that information, you can do some things. Here they have a little proof, and the proof says we have this isosceles triangle. They want you to prove that it's the altitude. So remember, altitude just means it's perpendicular. So the thought process behind this proof, I'm not really going to get into it too much, but the thought process behind this proof is they give me that is isosceles, so I know this side and this guy is the same. They also tell me that it's the median, so I know that this guy and this guy is the same. I can use reflexive to say BD is congruent to itself, so I can say both triangles are congruent because of side, side, side. Then I can say that these two guys are the same because of CPC-TC. I also say that they can form a linear pair, so using the linear pair postulate, they're supplementary. And so if they're supplementary and they're congruent, then they both are equal to 90 degrees. And since they're both equal to 90 degrees, that makes them perpendicular, therefore making right angles, therefore making they're right angles, thereby making them perpendicular, thereby making them a perpendicular bisector. You can also use that logic to say, okay, if these two guys are the same, then these two angles are the same, and therefore this is the angle bisector. I can also say that they're perpendicular and just add on to the fact that they're angle bisectors as well. So here they have that this is isosceles, and this is the altitude. And it says, what else do I know about Q? Oh, well, if it's the altitude, it's also the median. It's also the perpendicular bisector. It's also the angle bisector. They want to know what P is. So if I was just to write this down here, this is the origin. This is Ara. And this is P. Well, I know that the distance from here to here is H. So then the distance here from here to here is also H, but it's going in a negative direction. Right? This is going in the positive direction, so it's positive H. This guy is going in a negative direction, so it's negative H. So if I wanted the coordinates, it would be negative H, 0. Since I know that this is isosceles, I know that this altitude is also the median, and so it's also et cetera, et cetera, et cetera. So these guys are the same. All right, you guys, and that is the section. Hope you have a great rest of your day.